Good morning, everyone, and thank you for joining in. Scott Drennan will be presenting Eliminating Meshing from Gas Turbine and Burner CFD Simulations. Alrighty, and just a bit about Scott. Scott recently joined us here at Convergent Science as the Director of Gas Turbine Applications. Scott recently worked for Reaction Design, helping gas turbine and engine companies take advantage of more accurate chemistry. Scott has also worked as the gas turbine product line leader at the Electric Power Research Institute and as the R&D manager at Burner Company. Scott has a master's in mechanical engineering from UC Irving. Alrighty, everyone enjoy.
Great, thank you very much, Eliza. It's my pleasure to be here this morning for, frankly, our first inaugural webinar here in the Convergent Science webinar series. As Eliza mentioned, we'll be talking today about eliminating meshing from gas turbine and burner combustion CFD simulations. We have over 200 people attending this webinar today from all around the world, from North America, Asia, India, and Europe. So I welcome all of you. Good morning, good afternoon, or good evening, whatever time of day it is for you. Let's do just a little bit of housekeeping before I get started. The webinar will last a little more than half an hour, perhaps closer to 45 minutes. You'll have the opportunity to ask questions during the webinar. So here you can see the way that you'll enter any questions in during the webinar. It's in that little question box on the webinar tool that you see there. Go ahead and type in the questions that you have. I'll do my best to try to keep an eye on those as I'm talking during the webinar, and I'll try to address some of those questions at the end. So we'll take approximately a full hour, with the first 45 minutes being an audio portion of the webinar. So let me go ahead and get started here. So we'll talk about some of the topics I'll cover today. I'll cover who's Convergent Science. You may not know who we are, so I'll give a little background on who we are. I'll talk through some of the meshing strategies that we hear about people using for gas turbines and burners, how they've used those strategies, and perhaps some of the issues they might have run into leading to the desire to eliminate meshing completely from CFD. So then I'll go into how you can eliminate that meshing using CONVERGE. And I have a demonstration I'll show you today. It's a liquid-fired aviation gas turbine. So I'll show you some images of that and show you what it looks like in the software as well. Then I'll talk through adaptive mesh refinement, which is a technique we employ in CONVERGE to capture things like flame fronts, regions of high shear, regions of any high gradient. It's a key feature in the approach to eliminate meshing, or to develop the best mesh for the solution. Then I'll talk through some of CONVERGE's combustion and detailed chemistry capabilities. I'll give once again another little demo of a supercritical jet in a crossflow. And of course, everyone's interested in high performance computing and parallel computing. I'll touch on that as well. So let me go ahead, talk a little bit about Convergent Science. Convergent Science has been around almost 15 years now. I've been spending over 10 years developing the CONVERGE code. In 2008, began selling the CONVERGE code commercially, predominantly to the IC engine or automotive engine industry. But recently has been applying CONVERGE outside of IC engines. Part of the reasons why I've joined Convergent Science to look at gas turbines and many other different industries as well. Frankly, anybody that has a complicated geometry that's tired of developing meshes for it, CONVERGE is a good code for them. So certainly gas turbines, what we're talking about here today. We've also got chemical processing or turbo machinery, the petroleum industries as well. And then we're actually finding a lot of interesting applications in clean energy applications. And about 20 minutes into the webinar, I'll talk through one of those applications as well. So stay tuned for that. I'm speaking to you today from beautiful downtown New Braunfels, Texas, here in the center of the country, and up a little further north we have the headquarters up in Madison, Wisconsin. We also have offices in Europe and then in India as well, and China and Japan. So we really do have worldwide coverage. Let me go ahead now and begin the nitty-gritty of the webinar here and talks about how meshing slows down the CFD workflow. One of the benefits that I have and we have here is we get the opportunity to talk to a lot of different design companies and how they are using CFD and what their workflow is and where they would like to improve it. And of course, at some point in time when you start a CFD design project, you think about what geometry to use and you import that geometry. And then traditionally, it goes in, and I did use the black box there intentionally, it goes into a meshing process. Sometimes that meshing is done by the actual CFD engineer, but we actually find much more often that meshing is frankly requires a certain kind of expertise, and often that's done by a specialist that's a specialist in meshing. Then, of course, once you get the mesh set up, or get the mesh, you can then set up the case and solve the case, and that's a typical traditional CFD workflow. So things that we've heard about that is it might take about a week to decide exactly what geometry to use, and then you go into meshing. And what we hear is that often takes between a week to a month or more. In fact, just recently I heard 4.5 months to develop a mesh for a real complicated gas turbine combustor. So that's really an area that people are looking at and saying, is there a way that we can improve this, a way that we can reduce this, and frankly, as I'll try to show you, how you could potentially eliminate this meshing step. If you look at the setup of the case, typically that takes a couple days in almost any CFD code. And then solving, traditionally, of course, everyone would like to have the solution overnight, but often we're running solutions that are about a week in time. So once again, if you look at that time frame, that meshing piece stands out as a piece that's not only time-consuming, and does require specialized expertise. So that's an area where a lot of people are interested in trying to focus some attention on trying to improve. So let's talk through some of the modern meshing strategies that we've seen for other approaches in traditional CFD. You certainly might have seen some mesh like this, very highly skewed static meshes that are used for very complex geometries. One of the benefits you get from that is that seemingly you get very, very good mesh resolution near walls and things like that. Often, though, what ends up happening is as the mesh is adapted to these complex geometries, you end up with high cell counts, which can slow down the simulation. Perhaps even more important, though, those highly skewed cells really do generate some numerical diffusion and frankly can slow down the simulation as well. So and one other key thing that I've always struggled with is when I did meshing is I felt that I had to know what the result looked like in order to develop the best mesh. In this case, they've developed fine mesh right around boundaries, but perhaps there's something going on out here in the flow that's important that you really haven't got proper meshing for it. So you kind of have to know what the solution looks like before you develop that optimal mesh. And because it's a fairly, meshing is a fairly a complex technique requiring some expertise, many companies have outsourced that mesh development either to other companies or perhaps into other divisions that are located perhaps even on the other side of the world where you have these experts that can put together these meshes. One challenge you have with that is it frankly removes the CFD engineer one more step away from that geometry. Rather than the CFD engineer working directly with the geometry, it's the meshing person that does that, and the CFD engineer really takes what the meshing person gives them. The other thing that happens is maybe a little more subtle, but important nonetheless, is that there's a discontinuity in the CFD timeline. I always remember when I looked at CFD results thinking I'd like to make a change in a geometry and everybody agreeing it was a good idea to simulate that, but then I'd have to kick it to the meshing person and maybe wait a week to a month to get that back. And by the time I got the mesh back, I perhaps had already moved on in my design, and so I lost control of the workflow, and I felt like that sometimes would hinder my creativity or even would stop me from looking at new approaches because it just would take too long to mesh it. So I think that's one of the other key points is that with a lot of these complex meshing strategies, the CFD engineer really doesn't have control over it. So let me talk now about how you can eliminate meshing with Converge. Now, you may say to yourself, really, are you serious? You can actually eliminate meshing? Well, I'll show you how you can do that, and I'll show you why. Not only do we believe it's accurate, many other people do as well, and I'll show you some of that. So I'll talk through an aviation gas turbine combustor here. So this is a plain vanilla aviation gas turbine combustor, model combustor, just a very simple can with a number of different primary holes and dilution holes on it. The things I'd like to point out to you is that there's fuel going down a single atomizer. The model includes two zones for air, one going through the core, the other one going through an annulus, as typical lean direct injected combustors are. The model also includes these diffusion cooling holes in it, so we'll actually focus in on what happens as we simulate those diffusion cooling holes and how the mesh adapts to handle that. It's important to point out that the geometry includes not only this mixer in the front and the atomizer and the liner that you see, but also the casing, which I don't have shown. So all the air is dumped into the casing, and it decides to go through either the mixer or whatever hole in the liner it wants to go through. So that's not specifically specified. Converge calculates that. Let me go ahead and show you what Converge looks like here. Here we're showing the Converge screen for Converge Studio. This is the graphical user interface that allows you to manipulate all of the input files that Converge uses to do the simulation. Myself, I like graphical user interfaces, so this makes me happy. For those of you who really like to just work in command line and with input files, we have those as well, so you can do that as well. But let me give you a quick tour of what Converge looks like. Here we have the 3D viewer window with that combustor on there. I have read in this geometry, and what you can see are the little triangles on the geometry that come in from the STL file that we use to define the geometry. Let me go ahead and turn off that outer wall so you can get a better idea of what the actual combustor geometry looks like. Once you've read in the geometry, you have the ability to do diagnostics on that geometry, and one of the things you can do is take a look and see if there are any things perhaps that you need to repair. And we can take a look at the diagnostics, as we call doc, over here on the right. If I had any problem triangles or any regions that were not connected or watertight, Converge would identify those, and it would identify those with a little red square there, and it would tell me that there was some problem there that I had to address. And I have a fairly full suite of tools in order to address any repairs that I need to perform. Perhaps I need to stitch a couple elements together or align things together, patching certainly as well. I've got a number of different things I can do to try to get this geometry ready for us to do the simulation. Another thing that I have here is I have the ability to actually create different geometry elements. So perhaps you don't have a geometry you can import. You can actually draw fairly simple shapes like cylinders or cones or rectangles or boxes, and you can link them together to create a fairly simple geometry. So that's another option you have for you. So in this case, everything's okay for me, and I'll just go ahead and turn off these edges so I can show you a little bit more about what what this actual case looks like. Like I said, we're modeling each one of these diffusion cooling holes, and if I dive in on them, you can see that each one of them is represented here within the model, and that's good as well. One of the next things that we do when we're setting up a case is we go ahead and we look at setting up all the different setting up the case. And so let me go ahead and walk through the work tree that we use to do that. So as you can see, I've got all green checks here on the right because I've actually got this case all set up. But this is the work tree that you'd like to follow and try to get green checks all across the board. But it's graphically driven. You just go right through each one of these different parameters that allows you to set up the simulation parameters, decide what boundary conditions are, set initial conditions, and things like that. And that's also where you would set grid control and some of the controls that we use to manipulate the mesh as it's created automatically. So that's really very simply how you would set up a case within Converge. Once again, you just read in the geometry, try to clean up any issues you have with the geometry, and then you're ready to set up your case and run it. A couple other things I'd like to show you that come with Converge Studio that may interest you. Here is the mechanism reduction tool that we have within Converge that allows you to take a mechanism and reduce it for specific conditions and trying to optimize it for certain targets. In other words, perhaps you want to make sure that ignition delay is kept accurate over a certain range of temperature or pressure or equivalence ratio. This allows you to do an initial reduction on the mechanism before you even start running Converge so that you're using an optimal mechanism size and accuracy for what you're trying to do. The other thing that you have is you have the ability while a case is running, you can do XY line plots of the results to see what's happening with the simulation. So you can do full like I said, line plot visualization there as well. And then just recently we've added a full-blown version of Insight within Converge. So this is Insight for Converge. And that's what we use to generate all the 3D images. And in fact, I'll show you some videos that we've created now from that CFD case using Insight. So let me go ahead and I'll go back to the presentation. Once again, we're looking at an LES lean direct injected aviation gas turbine combustor case. We're looking at flow goes from right to left. Each one of these surfaces are colored. It's an ISO temperature surface that's colored based on the NOx that it's seeing. And then you can see a slice down the center line that's visualizing temperature. So let me go ahead and start the video and you can get a feeling for the kinds of visualization that you can get on the combustion that occurs within Converge. And once again, in this case, we're using the LES combustion model, but you also have the choice of using an unsteady RANS model as well. So that, once again, just gives you an idea of the kind of results that you can visualize from doing these kinds of simulations. And once again, that was built all using Insight here within Converge. So let me come back and talk a little bit about, now that we've talked about how Converge handles the reading of the case and how it eliminates that meshing, just from a top level here, if you take out that black box, you get to a much faster workflow. And one of the things that most users really like about it is that they have complete control over that mesh, and they really have complete consistent control over the CFD workflow. So they get the geometry from the CAD drawing. They're the ones that take that geometry, set up the case, and they run the solution and do all the results. So there's no discontinuity of going off to the meshing factory, so to speak. Whoops. Let's now talk about how Converge does the automatic meshing. There are some specific capabilities that Converge has that allow the automatic meshing to work not only effectively and accurately, but efficiently. One of the key things to point out is that we're using an automated mesh. It's Cartesian and it's orthogonal. So it should minimize numerical diffusion, should also be much faster than a highly skewed mesh. We use a cut cell approach at the boundaries, and then most importantly we apply what's called adaptive mesh refinement, where that we refine the mesh frankly where the action is happening in the CFD case. So if you have areas of high gradient, like let's say I'm looking at right here, you start off with a baseline mesh size or a base mesh size, and then that is adapted automatically based on gradients. Perhaps those are gradients of temperature or those are gradients of species concentration, but they could also just as easily be gradients of velocity, shear, or swirl, or things like that. But the key point is that Converge automatically adapts the mesh to resolve as best as possible that phenomena to get the right calculation. There's another approach that Converge uses called fixed embedding, and that's either around geometry features or other areas like sprays or areas where ignition might happen, and I'll show you what that looks like in just a second. One other speed-saving technique that Converge has is you have the ability to do on-the-fly grid scaling, which means you can start off with a fairly coarse mesh and then scale that to your mesh that you want to use in your simulation as the simulation settles down. So you actually get to a result faster because it's an easier or more gradual way of getting the simulation going. Another key point that we'll make here, maybe it's not as important for gas turbines and burners, but when you have moving boundaries, it's important to point out that the mesh stays stationary. It doesn't move. It stays where it is, and either the mesh grows in size or reduces in size as boundaries move. So that's a key point. Last point I'll make is it's regenerated at every time step. It doesn't take much computational speed to do that, and it is regenerated every time step. So there's no user meshing time. Our users consistently tell us that they really have gone from where they spend a lot of time in meshing to not doing any. We can handle complex geometries. Like I said, I'll show you an example of that in just a minute. Another key thing that people like is user-to-user variation, or as I call it, engineer sensitive. If you have two different people create two different meshes for a CFD case, and they do it by hand, and no matter how good those engineers are, often you'll find user-to-user variation, and that just really kills the efficiency of a CFD design group, because you end up spending questions about who has the more right answer rather than trying to understand why that answer helps you in your design. This adaptive mesh refinement really helps drive efficient cell use. You can have, like in this case here, where we've got actually a screw pump compressor, you can have fairly big cells out here where you don't need that mesh, and you can use either embedding or adaptive mesh refinement to put the cells really where they're needed. And there's no deforming of the mesh. It's like we said, it's static and it maintains its fidelity, and that really helps once we get to the parallelization. So you might ask us, of course, well, prove it to me that the mesh is good and it works, so the approach works. Well, a lot of people have looked at this. A lot of good companies. Here I'm just showing a couple of them. We've got some papers, technical papers on this. Of course, they're from the IC engine industry, but some very, very smart people looking at CFD and trying to understand where is the mesh dependency and how well does Converge handle mesh dependency. And so, like I said, we've got papers to back it up. So please let us know if you have any questions in that area. Let me now talk about, I just did talk about adaptive mesh refinement. And here shows some examples of adaptive mesh refinement. In this case, I'm showing an example of a slice through that lean direct injected combustor. And this gives a good example of the two different types of refinement that we have within Converge. The first one is, as I said, the adaptive mesh refinement, and as you can see, the base mesh size has been refined near these regions where the spray is, the regions of shear where the spray is, and also the regions where combustion is occurring. And that happens at every time step. Once again, you also see the embedding that we have applied around certain geometric features where it gets a little finer near those geometric features. And because we're using an octree approach, you still have excellent quality of that mesh near the boundary. And once again, we're using a cut cell approach near the boundary. Let me go ahead and show you an example, a live video that really shows how adaptive mesh refinement works within this gas turbine combustor simulation. Once again, you got to slice through the center line. If you look at the image on the right, you can see the spray coming in with the red particles, and you can see how at each time step the adaptive mesh refinement is calculating where that flame is, how that flame front may be propagating, and how it's influenced by mixing. You can also see things like the embedded mesh around these wall jets that we have, and also how those wall jets are being influenced by adaptive mesh refinement there as well. And there's a better close-up of that moving dynamically here in the lower left corner. So we think that's a key capability of being able to get to automatic meshing, is being able to have the state-of-the-art adaptive mesh refinement. I got another video for you here, and what we're going to do is we're going to focus in on this little box here on the middle of the bottom of the screen. That is of these effusion cooling holes. Remember those little tiny holes that are drilled to cool the air. We've actually got not only embedded mesh around those, but also adaptive mesh refinement working on those as well. And you can see how that works in this video. So the embedding is that we knew we needed a little bit finer mesh near there, so we just said put finer mesh there. And then we let the adaptive mesh refinement decide whether or not it needs to even refine that further. But you can see dynamically how that is used within the code. So let's talk about combustion and detailed chemistry, and I do have an example on this one, but let me just talk through some of the models we have available here within CONVERGE. It's fully coupled turbulence and chemistry. It's mixing, control, combustion. We got flame propagation. You can use it for emissions formation and ignition modeling. Look forward to doing future webinars to talk about lean blow-off and extinction. And what we're looking at here is a jet in a crossflow, a supercritical jet in a crossflow. So flows going from the left to the right. And here's another excellent example of not only the adaptive mesh refinement, and you can see how that's being applied as we move the video, but also how the detailed chemistry has predicted auto-ignition. In this case, the colors are temperature. And you can see that that flame is continually igniting. And as a designer, I have always wanted to really do some analysis on where the flame is stabilizing, what are the structures near the flame that are stabilizing, and this really gives you a chance to dive deep into those details and understand really what's happening within the flame. So detailed chemistry, everybody's interested in running more accurate chemistry. There is more accurate chemistry available today, but usually the challenge has been in trying to run it in CFD. In CONVERGE, you have a couple different things going for you. You have a mechanism reduction utility that I talked about before, that you can sort of optimize the mechanism you begin using while you are running the simulation. Then we've done substantial improvements to the speed of our SAGE chemistry solver, and you can see some of these improvements over here using fairly big reaction mechanism. It is a diesel mechanism, but the point being that really have dropped down the time that's required to do these complex simulations, even with really big reaction mechanisms. And there's some approaches that we've done in order to do that. A couple of them are, of course, chemistry's parallelized, but it's fully parallelized with excellent scalability in CONVERGE. We also have dynamic mechanism reduction that reduces the mechanism based on what's required in the local conditions. So that's another key feature that helps give us that acceleration and being able to handle larger, more accurate chemistry sets. And this all gets us to the point of being able to predict emissions. Also gets us to the point of predicting things like extinction, ignition, and lean blow-off. These are all key features. And then also ultimately getting to the point of predicting soot emissions. That's another key capability. It really requires some advanced chemistry as well. We do have a lot of discrete phase models, as you might expect, coming from the IC engine area. I show a picture of an IC engine here. If you just like to inject particles of a certain size distribution, like most gas turbine and burner people do, then you can certainly do that as well. If you really want to get into modeling what happens within the atomizer, you can do that as well. We have droplet collision and coalescence models, certainly turbulence dispersion. I also have a liquid wall interaction model. It's very important in IC engine modeling that may be of interest to people in the gas turbine side or burner side. Turbulence models, we've got, certainly have our list of turbulence models, not only RANs and LAS. I showed you a lot of LAS models today, so certainly we have those capabilities as well. Let me show you a video now as we move a little bit away from combustion, talking about fluid structure interactions. It's kind of a fun video since the baseball season just ended. We have to tip our hats to the Red Sox, but here's an example of a spinning ball, and you may have seen these spinning ball simulations before. The difference here, though, is we're actually doing a couple things that are different. We're moving the ball in space. That's one thing. The other thing is we're taking the effect of the swirling ball and its the pressure differences on it to actually move that ball in a direction like a typical curved ball would. So that's an example of how you can use not only moving geometries but fluid structure interactions in Converge. I've talked a couple times about how we've used complicated geometries, and one of the key features Converge has is to be able to accommodate those complicated geometries. Here's a non-combustion example, but I think it makes the point that I'm trying to make. Here's a couple wind turbines, and this is the way that we set this case up. We went and looked for some geometry file that described this little canyon here, cute with a little waterfall too. We found another geometry file that described what a wind turbine would look like and imported that. Cut off the blade and let it spin and define that. Copied that 3 other places and located those there. And then actually threw a truck in there. We picked up a geometry of a truck and dropped the truck in the simulation and to see what its effects are. And so here's an example of how you can really just very quickly and easily import geometries into Converge and set up a simulation and be running very quickly. What we're showing here is a slice right through the center line of one of these jets, or excuse me, one of these wind turbines, and you're seeing the impact of that wind turbine on the turbine behind it, and then you're also seeing the impact it might have on that truck there. So like I said, it can be very fast. The addition of that truck to the model took 5 minutes. Once we had the STL file imported, very, very easy to set up the boundary conditions and its motion as well. So here's an example, a real example of some pretty complicated geometries, albeit not a gas turbine combustor, but some things that Converge can handle. So let's talk about parallel computing and Converge. Certainly has been parallel for a long time. A lot of people using it in high-performance computing, using the MPI technique in automatic domain decomposition. We're very mature in our load balancing and have really worked to maximize or optimize memory usage. So it's not the first year that we've had parallel processing capability. We've been through some of those growing pains and really have optimized how it accounts for parallelization. And it also, of course, works with the discrete phase, and combustion is fairly parallel, as well as being able to handle stationary and moving boundaries in a parallel environment. So once again, it's not just us that say that. There's a number of other people that are using it. Here's an example of a paper written by our friends at Oak Ridge National Laboratory and DOE, and talking about using Titan and using Converge and truly getting to predictive CFD, which is really where we all would like to get to. Another thing that I'll touch on just before we close is an optimization approach that we have within Converge, a tool called CONGO. It's a genetic algorithm, and essentially what it does is it helps you do a design of experiments, and it does it automatically. So it kind of helps you think outside the box and dream up or identify certain ranges of variables. By identifying merit functions and design constraints, it tries to optimize what these merit functions are within those constraints. So functionally, it can be used to look at fuel-air splits between primary between core and maybe premixed to get an optimum NOx and CO, because those are two variables that work against each other to a certain extent, and there's always an optimum between them. Then also flame location. Perhaps you want to try to get flame location at a certain point. And then pattern factor, the exit temperature factor that you see, the ability to move holes or jets or cooling strips and things like that in CONVERGE can be very powerful, used with CONGO to try to get, let the computer think of what the best design is and do that optimization. So in summary, you made it to the summary slide. Meshing can be eliminated from Combustion CFD. I've shown a number of examples in that. As I said, we've had a lot of experience on the IC engine side where CONVERGE has really been adopted as the primary tool for Combustion CFD, and what we hear from them is that they're getting a revolutionary improvement in their workflow by eliminating meshing, not only from improving the timeline, shortening the timeline, but also improving the quality of the CFD product. And CONVERGE is a full-featured CFD tool, and it does have this ability to eliminate meshing. So that's the other thing I wanted to try to point out, is that it is full-featured. It is a mature and robust code. It's been used for quite a while by some pretty discerning customers. So a couple questions for you here at the end, just to think about is, do you have complicated geometry? Do you want to eliminate meshing? Perhaps those are two of the reasons why you chose to join the webinar today. And do you want to include more accurate chemistry? And I'd say if those answers are all yes, then take the CONVERGE challenge. Give us a call. Give us a day and we'll show you how you can eliminate meshing. It might not be the right thing for you, but give us a call and we'll give it a try. So go ahead and go on convergecfd.com, fill out an inquiry on there and let us know, and we'll come by and we'll see how well it works for you. I've got a couple other things I'll point out here. CONVERGE has a family of software. There's the CONVERGE solver here at the core. I showed you what the graphical user interface CONVERGE Studio looks like. If perhaps you don't have the computational resources and perhaps you're looking for an entry-level starting point to initially get started on doing CFD, we have CONVERGE in the cloud. All of those will use CONVERGE as its core solver. This is more for IC engines, but we also have CONVERGE Lite that comes for free with Gamma Technologies. And all of these use, like I said, CONVERGE as its core solver. Check us out. Check out CONVERGE and Convergent Sciences. Got 3 pages I'd like to point you to. Facebook. Here we're on Facebook, believe it or not, and go ahead and check us out there. Also LinkedIn. Please check us out there as well. We've got a page on LinkedIn, and then check our webpage out. We just had a major improvement, we believe, to the webpage, or at least that's what people are telling us, and so go check it out. We've got some new information on there and downloads and things that you can look at on the webpage, so go check it out. We are, like I said, this is the first in a series of webinars we're going to do. This is one, we're talking about gas turbines and burners. Here are some upcoming webinars we're planning. Lean blow-off and extinction, NOx and CO emissions, soot and particulate matter, ignition and sprays, and fuel effects. And then also for IC engines, we'll look at advanced sprays and NOx modeling and alternative fuels, and then soot and particulate matter as well. So I'd say over the next year we plan on touching on each one of those topics, but please, if you have any input on either something here you really want to see or perhaps something that's not there that you'd like to see, send me an email or use that Facebook page or the LinkedIn page to generate a discussion on it. That would be great. So thank you very much. I appreciate you for joining the webinar. I see that there's been a number of questions that have been asked. So I'll take a quick peek and look at those questions, but I'm going to leave you with what I think is a pretty video here of an actual gas turbine combustor that we've done using Insight that we have within Converge. So I always like looking at, and that looks like a flame there, so I always like that. So I can see that over here on the question and answer, or questions, we've got a couple of questions that are common, and a number of people have asked, and so let me see if I can touch on those at this point. Here I'll turn off the video so I don't get a little crazy. First one is, the question is, will I spend more time setting up the geometry, getting it ready for automatic meshing, as I might as well have just gone ahead and done the meshing? Is it really a time savings? That's a good question, and that's a fair skepticism to have. But from our experience, certainly the first time somebody reads the geometry into Converge, there can be some issues with the geometry not being watertight or perhaps being dirty. But most often we find that those issues can be resolved relatively quickly. And by the time they go around once or twice of receiving geometries from their CAD department, you really can identify exactly what you need to get from them in order to minimize the setup time in Converge. And quite often we find that you can replace geometry elements or read in a new element and get it set up to run in minutes as opposed to days or weeks. So that's the reason why I said give us a day and we'll show you what it looks like. The other thing a number of people have asked about is, and we do hear this a lot, people that have had years of work with Fluent and using user-defined functions in Fluent and trying to get reasonable results, that approach. And so they feel that, gosh, is all the work that I've done trying on user-defined functions, will that be lost if I switched from Fluent to another code? And the first comment I'd always have is, do we really need some of those user-defined functions? But you also certainly have the ability to use your own user-defined functions in Converge. So if it is a function that you really feel is important and you've got some secret sauce, you do have the capability to use user-defined functions in Converge. And then I'll just answer one more question here. The question is on what kinds of mechanisms can you run in Converge? And perhaps I hadn't mentioned that before, but Converge reads in mechanisms that are in ChemCin format, should be able to run any of those mechanisms within Converge. And of course, I have to mention that you have to test the quality of the mechanism that you're using, because that's a key part of the simulation. But there's no special formatting you need to do with any mechanism in order to get it to work and Converge. So I think I'll just conclude the audio portion of the webinar right now. There are still some people sending in questions. Go ahead and continue to send those in. I'll keep that open for about another 10 minutes. But I will stop the audio portion right now. And once again, I want to thank you very much for being here and being involved in this webinar. And I look forward to talking to you in the future. Thank you. And we will post this webinar. We'll send out an email and let you know when the recording has been posted. Okay? Thank you very much.